So we're going to go dealing with data. Oh, come on. Let's go, pen. There we go. Dealing with data. Whatever you want to say. Data, tomato, tomata. Garage, car hole, whatever. Okay, dealing with data. So in science, we like to come to conclusions based on data. Okay, so what counts as data? That's interesting because depending who you ask, people like to try to shoehorn lots of different things into being data. Okay, so in one sense, data can just be like your basic observations. Okay, just observations could be data. And that's fine. You can tell some interesting things from just your observations. And then there's numerical data. Or like if you want hard data. And this could be like soft data. So when we're talking physics, physicists tend to the realm of hard data. Okay? Social scientists will often tend to the realm of soft data, although they do try to use hard data when possible. Sometimes it's just difficult if you're like observing people's behavior, et cetera, et cetera. It's hard to quantify that. It's easy to quantify things like masses or velocities or, lengths and all that sort of thing, all right? So it's easier for a physicist to use hard data because what we do tends to generate numbers, hard numbers, verifiable numbers, okay? So we want to know if we get some hard data, if we do an experiment, we generate hard data, well, now what? So I think the best way to do this is just to grab some data and deal with it. Okay, so I just put a little chart in here. And what we're looking at here is some data that we've collected. And it's important here to note a couple of things. Okay, so first of all, dependent and independent variables are always going to come into play here. All right. So dependent variable in this case, we're going to find is this guy. It's our dependent. Okay. Dependent variable is going to be your y value when you graph this data, and your y value when you figure out a way to relate one side of the equation or one side of the data to the other side of the data. And this is our independent variable, which is our x. So remember this. What we're doing is we're changing. We as the scientists are changing or varying our independent value, okay? And as a result, what is happening over here is changing, okay? So let's just see what we mean by that. So basically, essentially what we have is this situation. I'm varying the radius of a circle, okay? I'm varying the radius of a circle, and we're recording over here how the area of the circle changes, okay? So we're using an example that you should already more or less know the equation for, but we're going to derive the equation from the data rather than going the other way and just having that equation and using it. So I think most people will recognize what equation we're going to get out of this, but let's do a little bit of background here. It's nice to use one we're familiar with so that we can kind of like have in our mind what to expect. But let's just talk about the types of relationships we might see if we're to graph our data, assuming the two things are related in some way, okay? The sort of standard one, the first type that you always will learn is just one that looks like that, okay? Straight line in some way. It might be there, it might be here, it might be here. We describe this generically as y is proportional to x. If y grows 1, or if x grows 1, y grows as well in some proportion to that value. It might be 1, it might be 2, whatever, okay? That's just a proportionality. If you're unfamiliar with a proportionality, here's a proportionality. If this is a scale, okay, and I start putting apples in here, say at the supermarket, okay, or some like relatively uniform value, what the scale weight is proportional to the number of apples I put in, right? So weight is proportional to number of apples. Does that make sense? I know if I put more apples in, I'll get more weight, but I'm not saying that it will equal some value, okay? If I know, say that the average apple weighs like 200 grams, then I could say this: weight equals 200g times number of apples. If I know that, if I know that's true, if I know every apple is 200 grams, then I could tell you exactly what the weight will be. This is not that. This is a proportionality that says generally, as I increase number of apples, the weight will increase. This is a truth. It's not an equivalency. It's a proportionality. It's different. Anything that has this relationship is saying y is proportional to x. If you have a straight line, y is proportional to x. If I graphed out the proportionality, this would simply be true, right? I'd go like this. I would say this axis here is number of apples, num apples, okay? And this is weight over here. So my dependent variable is weight, and my independent variable is how many apples I put in, all right? If I don't know ahead of time what the weight of a single apple is, and I don't weigh it directly, I could, from data, deduce what the weight of an apple is, and it will in fact be the slope of this line, won't it? It'll be the slope of this line. The slope is like the 200. Once I have the slope figured out, I can actually convert it into a y equals mx plus b value. In this case, when there's no apples, there's no value on the scale, assuming the scale reads 0 and there's nothing in it, right? The y, right, represents the weight. The m represents the mass of a single apple, and the x is the number of apples that we have, and we get that, okay? We're simply dealing with the generality that if you have a straight line, y will be proportional to x, period. That will be described in individual cases, however, with an equation relating the two values. Y equals mx plus b looks like this, okay? Now, a variation on this is a negative relationship, okay? So in this case, y is proportional, oops, I guess I better draw the actual line in there. Y is proportional to a negative value for x. Okay, so that's the general proportionality or the general relationship between these things. This could be like if I have a bin of apples, all right? As I remove the, oh, no, sorry, never mind. That's incorrect. Do not quote me on that. Okay, what we're saying here is this may be a better one would be like if I'm driving to the left, the longer I drive for, the further in the negative I get when I'm talking about, say, a velocity, all right? And the equation for this is going to be that y is equal to negative mx plus b, or m times negative x plus b, all right? An example of where you would see this is, displacement is equal to negative v times time if I'm traveling to the left. That's where we've seen that before. Okay, so continuing on to slightly more complicated versions of this. And by the way, if your data, right, so you're going to collect data, like this, okay? You might, because it's real data from real life, you might get like data points in your scatter plot that don't necessarily all line up perfectly in a straight line. So from that, you create what's called a line of best fit, right? So line of best fit. Basically, it's sort of like an average. Now, we'll get into the nitty-gritty of creating this and how you do with error bars and all that sort of stuff later. But for now, just realize that real life data sometimes is a little bit messy, and you just get the best line you can from your data. Sort of rule of thumb is if there's 2 above, there should be 2 below, or 3 above, there should be 3 below. Okay, this is at your stage a bit of a judgment call. There's software and so on that can help you make a line of best fit. If you're doing it by hand, it's a bit of a judgment call. Okay, so moving on. You might also encounter graphs that look like this. Or data that works out to follow this type of a path. Remember, right? You're going to graph your data points, and you're going to do a line of best fit. So this is an exponential relationship of some sort. So this is where y is proportional to x raised to some power. Okay? They all look the same, all right? Whether this is x squared, x cubed, x to the 4, very rare, but maybe it happens somewhere in physics that I don't know of. If you have that, okay, it's going to be curved in this way, all right? This is an exponential relationship of some sort. So x raised to the power of n. And then you could have its counterpart, y is proportional to negative x raised to the power of n. Okay. The last kind that you might possibly see would be one that goes like this. Oh no, this isn't the last kind. Sorry, my mistake. And this is where y is going to be proportional to the root of x. Okay. And the last one you might possibly see is this. This is where y is proportional to the inverse of x. Okay, so now it's time to deal with this. So the first thing we're going to do is we're going to make a graph. We're going to make a graph of this data. Now this can either be done on your calculator, by hand, or using a spreadsheet like Excel. Okay, so hand, spreadsheet, or calculator. Because you can't really see me using my calculator, it will crash this program. I will use a spreadsheet, and I'll pop that up right away. Okay, so there's your graph. We ran out of time here, so in the next video, we'll look at how we can pull a formula out of this type of information. So there's our data points, and there's our line of best fit.